Okay, hi everyone. We all know how difficult it is discerning a difference between ruby fountain and volcanic red on a Dulux colour swatch. But that's essentially what my PhD boils down to. I've been trying to detect tiny shifts in the colour of sunlight emitted during solar flares. These are massive explosions in the sun's atmosphere caused by rapid restructurings of the sun's magnetic field. I want to understand the dynamics of the sun's atmosphere during these events, whether it moves up or down, how fast it's doing so, and we can do this with something called the Doppler Effect. This states that the colour of light that you observe from a source actually depends on the source's velocity. If it's moving towards you, it looks a bit bluer, and if it's moving away, it looks a bit redder. So if you can calculate a shift in the colour, you can actually work out how fast that source is moving. Now when we talk about colour, what we're really talking about is wavelength, which is the minimum distance in space that a light wave takes to repeat itself. So the sun, like most stars, is mainly composed of hydrogen, and hydrogen, like all chemical elements, emits light only a few specific wavelengths, kind of like a chemical fingerprint. We call these narrow bands of light spectral lines. I measured the position of 4 of hydrogen's ultraviolet spectral lines during 6 solar flares with NASA's Solar Dynamics Observatory. Since we knew exactly what wavelengths these lines should have had, we could very accurately measure how much they'd shifted by during each flare by looking at their actual positions, effectively calculating a shift in their colour. I then used the Doppler effect to calculate the velocities corresponding to these wavelength shifts, and found that they suggested plasma flows of around 30 kilometres a second, sometimes upwards, sometimes downwards. That's plasma moving from Glasgow to Falkirk in 1 second. We're now using computer modelling and simulations to try and understand why we have plasma moving in a bidirectional way and not just condensing inwards. But why does any of this even matter? Well, during a solar flare, torrents of charged particles can end up streaming towards our planet, which can really disrupt our geomagnetic environment. In 1859, the first solar flare ever observed induced a geomagnetic storm so severe that the northern lights were visible from Hawaii. Hawaii is only at 21 degrees latitude north. So that wasn't really a problem back then. I'm sure it was a lovely show. But the people of 1859 didn't rely daily on GPS, satellites, telecoms, and the aviation industry. If a similar event were to happen today, we'd be in trouble. The government now includes severe space weather on its national risk register, and the Met Office has its own space weather forecasting centre. Ultimately, forecasting these things likely remains a long way off, but if we're ever to do it, we first need to understand the physics.